Hi folks, we're going to take a look at number 10 on page 345. So this asks us to find the equation to describe the set of points equidistant to these two given points, and then they want us to find two particular points. All right, so first thing to do is to set this up. So I'm just going to randomly pick locations for points A, so 2, -1, 3, and point B, 1, 2, -3. Okay, and what I'm looking to find are all the points that are equidistant. So obviously there's the one that's right in the middle, but I'll also have a point here and a point there and a point there, and I'll also have points going up that are equidistant to the two. So in order to just be as generic as possible, I'll just pick some point up here. Okay, say call it C, and since I don't know what that point is and they don't give me any information about the specific point. So we solved one where they told us it was on the y-axis, so we can narrow down what that point would look like, but here no information at all, so I'm just going to call the point xyz. All right, and I know that the distance between C and A and C and B is going to be the same, all right, regardless of where C is. Okay, now we don't have a specific distance formula between points, but we know that if we create a vector between the two, then the magnitude of that vector is just going to represent the distance between the initial point and the end point. All right. Now I'm going to choose to create my vectors in this direction. Okay, and you might remember why I decide to do that. It's because when I find the vector from one point to another, I determine that by subtracting the second component by this first component. So I'd rather write x minus 2, y plus 1, z minus 3 than write 2 minus x, -1 minus y. Just makes the algebra slightly easier. Okay, but the idea here is the equation that I'm going to use to solve this is the fact that the vector AC has to be equal to the vector BC. Okay, sorry, not the vector, the magnitude of the vector AC has to be equal to the magnitude of the vector BC. All right, so at this point here, I'm just going to start inputting what I know and see how far I can go with this equation. Okay, so the magnitude of AC, so it's going to be the square root of, okay, so remember AC, second minus first, so it's going to be x minus 2 squared. Okay, plus y plus 1 squared plus z minus 3 squared. Okay, and then equal to the magnitude of BC. So again, BC is going to be x minus 1, y minus 2, z plus 3. So the magnitude is going to be the square root of x minus 1 squared plus y minus 2 squared plus z plus 3 squared. Okay, and what we have is we have an equation. Okay, now it doesn't look like we're going to be able to solve for exact values of x, y, and z. It looks like we're probably going to have these variables in my final solution, but that's what they seem to indicate, that we're looking for an equation to describe this set of points. Excuse me. All right, so I'll start by squaring both sides. Okay, to get rid of the square root, so that's nice. And while I'm at it, I'll start expanding these binomials. I don't think there's any way around that. So I'll try to write this small here. So here we have x squared minus 4x plus 4 plus y squared plus 2y plus 1 plus z squared minus 6z plus 9. And on the other side, x squared minus 2x plus 1 plus y squared, minus 4y plus 4, and then plus z squared plus 6z plus 9. Okay, and what's nice about this equation is that, hey, if I subtract x squared from both sides, they both disappear. Subtract y squared from both sides, subtract z squared from both sides, they all disappear. So I've gotten rid of all the squared terms. So let me now bring together all the exponent 1 terms. So here I have -4x plus 2x, so that's going to be -2x. Here we have 2y, and we've got -4y, so if I bring that to the other side, 2 plus 4 is 6. Y, and then we've got -6z minus another 6z, so minus 12z. All right, and let's bring, I guess, all the numbers to the other side. So let's see what we have. We have 4 plus 1 is 5. 5 plus 9 is 14. Okay, and then here we've got, so that's going to be negative 14. Bring that to the other side. And here we've got 1 plus 4 is 5, plus 9. Oh, no, it's also 14. There you go. That worked out. So plus 14. So in the end, we end up with negative 2x plus 6y minus 12z just equal to 0. And in fact, if we want to clean this up a bit, we can divide both sides by negative 2. Okay, and we'll end up with x, and that's going to be minus 3y, and this is going to be plus 6z is equal to 0. So this is the equation that represents all the points that are equidistant to A and B. Okay, now you might want to start to think about the fact that this equation kind of looks very familiar, okay, except it's got an extra variable in there. And try to think geometrically what this represents in terms of what these points would create if you put them all together. And this is going to be the subject, a very big subject for us later on. So just keep that in the back of your heads. All right, now the other thing they want us to do is to find two specific points. Well, there's, I think, a really obvious one when you look at it, because if x, y, and z are all 0, 0 minus 3 times 0 plus 6 times 0 is going to be equal to 0. So, point 1, 0, 0, 0, that one's pretty easy. Okay, I'll even write it out, since 0 minus 3 times 0 plus 6 times 0 is equal to 0. Okay, now for point 2, there's no restrictions on these. So I guess one thing you could do is pick values for 2 of them and then solve for the third. So let's say I let y be equal to 1 and z be equal to 1. Then I can just calculate x. So x is just going to be equal to, well, 3 times 1, bring it to the other side, is 3. And then here, 6 times 1 is 6. Bring that to the other side, it's going to be minus 6. So it's negative 3. So another point would be negative 3, 1, 1. Excuse me. And you can check it again. Negative 3 minus 1 is negative 4. Plus, sorry, did I make a mistake here? It becomes positive 3 minus 6, so negative 3. So if I stick this in, I get negative 3. Oh yeah, there we go, sorry. Negative 3 minus 3 is negative 6, and then plus 6 is equal to 0. Okay, sorry about that, that works. Bit of a waste of time there. So just to recap here, I'm given these 2 points, okay, and I represent the point that I'm looking for by just some random x, y, z, and I use the fact that the magnitude of the vector from AC and from A to C and from B to C are going to be the same. And then from there, I reduce that to as simple a form as I can. Okay, that's it for this one.